Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Foundational Mathematics, we want to start to talk about integral calculus, in which we will try to sum up multiple small components of a function. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description. So also before we get started, I'm gonna separate this discussion into two parts. The first is we'll discuss about the basics, in which we'll define what is an integral and how do we solve an integral. And then after that, I will show you some tricks when you're doing integrals. So if you want to skip forward between all of these discussion, you could go ahead and refer to the timestamps shown here. So, we should start to talk about what exactly is an integral. So let's actually ask the question. If f is the derivative of big F, what is f? So this is a very subtle question in which we are asking about what exactly is the function before you derive it. So let's just do a simple idea in which f is a constant. F is a constant. And let's see where it will lead us. So if f is a constant, we can get this certain idea in which the function x will be the f x minus x0, and this is f x0 plus. So this is a very simple guess in which if you know what the function at x0 is, it will be correct, and then if you take the derivative, it will also make sense. But this is a very simple idea in which we assume that the function is constant. So from this idea, we could try to rewrite the function f again. So what is function f? It's f minus f x0 over x minus x0. And this is what you know as the derivative, as long as your x goes near to x0. So this is the same idea. So we just need to find a value which the function's derivative will become our small f. So that's the main idea when we're dealing with integrals. But we could also try to ask the question, what exactly is an integral? So let's just refer back to our equation in here. We see that we have f x0 plus the small function f x minus x0. So let's just refer into, let's say, a graph in which we have a curve, something like this. And we'll call this as the small f. So what this exactly denotes is that x minus x0, so let's just take this as x0, and then let's say you have an x which is very small. That means that you are taking this thing from x0 to x. So there is a small change in the x. And then you multiply this by the f, or pretty much the height. And what you get here is pretty much the area. So what you get here is the area of this small slit. But let's say if you know the big f x0, or pretty much a value in which you could add the small slit up, what you would get is the area of the curve. So it's pretty much the area in between the function f as well as the x equals to 0. So we could express this as fx equals to f x0 plus the sum of the functions in each of these xi's multiplied by the delta xi from I equals to 1 to n, let's say. n really depends on the amount of sections that you cut. But if you actually take your n to go to a certain value, let's say going to infinity, and then we'll just fix our endpoints, let's say from 0 to maximum value of x, and then we'll just divide these sections into equal component, we could actually simplify this notation into something which we will call as the integral. So it's the integral of function x dx from your starting point x initial to the final position x final. So this is the final and this is the initial. It's the same idea in which you have your function, multiply that by the small changes, and then you would get the area. And then if you sum them all up, what you would get is the area. Technically, it's not exactly the area. So here's the idea. Because we rewrite the sum as the integral, this is the same thing as the function x minus function x0. So this is x0 and this is the function x. So what we see here is not exactly the area at x, but instead it's the change of area. And so we could actually write this in a much more formal way. You could just write a bar here from x0 until x. So this will refer to our endpoints. So now let's ask a little bit of a question. So if we know what df over dx is equals to f, let's say, I could just state that the function is, sorry. So if we have df over dx equals to f, this is pretty much the same thing as df plus a over dx, which means that there are two functions in which its derivative will result in this small f. So wouldn't this affect our integral? And the answer is no, because here's the idea. If you take the integral from x0 to x of function x dx, what you end up doing is take the function x minus the function x0, right? Or if the answer that you get was this one, it's function x plus a minus function x0 plus a. And what you get is that you could cross out the a to get the same answer as before. So it doesn't matter what your function is, as long as the derivative of the function is exactly within the integral. That means that your answer is correct. You just need to put in your boundary conditions. And so this is why if we actually denote this as the integral of function x dx, this will be function x plus c. Since we don't have any reference point, so what we need to end up with is to add a c, in which the c represents initial conditions or particular conditions at certain points. So let's try to figure out some integrals. And by the way, you could actually get the results of integrals from a table in which it is already published within Wikipedia or maybe some handbooks. But in here I want to discuss a little bit about some functions as well as its integral. So an easy one is x to the power of n. What's the integral of x to the power of n? As long as n is, let's just assume this to be greater than 0. So if the n is greater than 0, what you get is this is pretty much 1 over n plus 1 x to the power of n plus 1 plus c. So you can just prove this. If you take the derivative, it turns out that it's the same thing. Well, it turns out that this would also work this will work for any value except for n equals to -1. So everything can be denoted as this. And then if you want to take the integral of natural log of x, if you want to take the integral of 1 over x, or x to the power of negative 1, the answer is the natural log of x, as long as the value inside is positive, plus c. So another example of the integral is probably the cosine or the sine. So let's try to figure out the integral of cosine x dx. So you could just guess the answer straight away, because you know that sine x, if you take the derivative, will become cosine x, so you could just guess this to be sine x plus c. And it turns out that it's true. So remember, since the integral has this constant here, that means that you need to add much more parameter into your function if let's say if your function x is this guy. So one particular condition is that you could assume that function 0 equals to a certain value or something else. And so with that, you could figure out what the constant is, so you could get the function for your integral, which is also following your initial conditions. So now I want to discuss a little bit about the properties. So there are multiple properties of integrals. So we can first discuss about the linearity, and I will prove this slightly. So the way that we'll actually describe this is take, let's say, AF plus BG, in which A and B are constants. Oh, that's that. There we go. So this is the same thing as writing this as a sum, right? Sum of AF plus BG delta x. And you pretty much take the limit, right? And so remembering about sums are linear. So you could just write this as something like this, plus b delta x, plus b to the sum of delta x. It should be something like this, g delta x. There we go. And so with each of the limits here, so pretty much limits are also linear, what you get is that this is a to the integral of f dx plus b to the integral g dx. So it's pretty useful if you're trying to separate or maybe even combine integrals together. So maybe within your handbook you don't have the integral of certain values. You could instead try to separate it, and then try to find what's the integral of this guy and what's the integral of this guy. The second property is about compositions. So the way that we'll actually discuss about compositions is if we have the integral from a to b of function x dx, this will be the same thing as taking the integral from a to c of function x dx plus the integral from c to b function x dx. So the idea is that if you have, let's say, the sum, and we want to figure out what the sum is, but unfortunately for certain values the result is going to 0 or it's going to some other value, or maybe you could even use your symmetric ideas. So what you could do is that you could just separate this and then try to compute this integral, and then you add it with this integral. So that's the idea. But this also brings another type of property. So if we just state the integral from a to a of function x dx, which we know this to be 0, you could just write this as the integral from a to b function x dx plus the integral from b to a function x dx. What you exactly get from here is that the integral from a to b of function x dx has to be negative integral b to a function x dx. The last property to discuss is the integration by parts. So how do we prove integration by parts? So let's try to remember about the chain rule, in which if you have the product rule. So if we have f and g, So let's just write this in big notation first. F and g. The derivative will be fg minus the plus gf. And let's just take, okay. So from here, with this notation, we could just separate everything out. Oh, sorry. This is the derivative of fg. So what we can get from here is that if we take the integral of everything, this will be fg equal to the integral of fg plus the integral of gf. So what we can do is that we could take the integral of fg, no, sorry, let's write it this way. The integral of big F g dx equals to the fg minus the integral of gf dx. So maybe this might not make sense. So let's actually do an example just to see how easy it is to use this property. So one example is the integral of x cosine x. So we will evaluate this from x1 towards x, and let's see. So we cannot truly guess it straight away, unless of course if you have experience. So maybe an easy way to do this is to actually separate this into two parts. So something easy to think about is that you could actually take the derivative of x straight away, and it's gonna make it much more simpler. So we can just denote the big F to be x, so the small f will be 1. So big F and small f corresponds to the integral as well as the derivative. And so for g, it will be the cosine x, following our notation here. That means that the big G here will be, let's just put a number, let's say sine x. It could be sine x plus c, but in here, just to make our life simple, we could just choose a solution that works. So we got this. So what we eventually get is that this integral can be transformed into f times g, or x sine x. Evaluate that, so this is pretty much the evaluated value anyways. x1 towards x. And this will and subtract that by the integral of the small f, which is 1, and g, which is sine x dx. So this will be x sine x minus cosine x, plus cosine x. Evaluate that from x1 towards x. So you could see that it actually makes it much more simpler. Let's do another example. Let's say we want to figure out what's the integral of the natural log of x dx. So this is a little bit harder to think about, but maybe you could think about something like this. I cannot truly figure out what's the integral of natural log of x, but what I can do is to find the derivative. So we could just write this down to be 1 over x. But then that means that our g should be 1, or our big G needs to be x. And what we get, this will be f times g, or x natural log of x, subtract that by the integral of this f times g, which is dx. So what you get here is x multiplied by the natural log of x minus 1. Evaluate that for certain values. So it's pretty useful if you're trying to solve a integral in which you don't know the integral, but you know the derivative. It could change the way of solving it. So we have already fully discussed about the basics of integration as well as their properties. But obviously you couldn't truly solve integrals only by guessing. You could make it much more simpler so that you could find it within your table. So let's try to figure out these niche ways of solving it. So let's just do one example. The integral of x squared over x cubed plus 4, everything squared. dx. I couldn't really solve this straight away, but maybe I can do a very easy thing to do, which is just assume x cubed plus 4 is u. And let's see what will happen. So let's just try to take the derivative of this guy. The du over dx equals to 3x squared. And what do we see here? It turns out that we have this x squared, so we could just substitute that with our du over dx. We multiply this by dx, divide the entire thing by our u squared. And this is still the integral of, let's say, x1 to x2. But maybe we could just actually state that maybe this dx and this dx should be the same. So instead, we will just rewrite this as 1/3 du over u squared, the integral, from the u of x1 and the u of x2. And this is negative 1/3 u, evaluating u1 and u2. So this idea might seem very, very intuitive, or maybe something that is logical sense. And it turns out that this is true. And we could write this in general. So let's just denote a function, let's say j of x over u. And we'll call this dx over du. So this is what we will call as our Jacobian. So we could write our Jacobian to be the integral, so we could substitute, let's say, function x dx. We can turn this into the integral of function x in terms of u, multiply that by the Jacobian of x over u, multiply this by du. So it's as if that we are doing the same thing, but we multiply this by dx over du. So the substitution in here doesn't have to be a polynomial. It could be a fraction, it could be trigonometric, or it can be multiple other things. So I will try to also explain each of these substitutions based on examples. So let's ask some questions that we could use integrals for. So we could try to solve the circumference of a circle, let's say. So the circumference of a circle is normally denoted as x squared plus y squared equals to r squared, right? This is pretty much our circle. And let's try to figure out its circumference. So the way that we could actually do this is to ask the question first. How do we try to sum up a certain function with respect to dx? So maybe the idea is that you could actually just take this one section and we could try to solve this one arc first. Because pretty much a circle has two components. It's this positive side as well as the negative side. So we could just solve for the first arc and then multiply it by 2, which makes sense. So this is y equals to the square root of r squared minus x squared. Evaluating that from negative r towards r. So we get the boundaries first with respect to x. But what about the function that we want to add? So we could think of this as taking very small components of the function. And we'll call that as ds. So each of these ds corresponds to two things, the dx as well as the dy. So this is defined to be the square root of the dx squared plus dy squared. But maybe we could simplify this much more further. Let's just instead divide everything by d. So technically this is the sum of ds anyways. So we could just take out the dx out. So it's dx over 1 plus dy over dx squared. So this turns out to be negative r towards r. So this is technically the reference starting from initial to final. Or if you have already substitute your ds, it turns out to be this guy. So it's dx over the square root of 1 plus dy over dx, which is 1 over 2 to the square root of r squared minus x squared minus 2x. So this is x squared over r squared minus x squared. So this will simplify into, so we could just do the integral again. The integral of negative r towards r of r over the square root of r squared minus x squared. So it's everything multiplied that by 2. dx. Now, remember that basically you could actually take the r out because integrals are linear. So you could simplify this into this type of integral. Now maybe you could refer to your handbook to see what's the integral of this guy. But maybe a clever way to solve this is by using substitution. We could just substitute x equals to r sine theta, and let's see what will happen. So we should also try to change our boundary conditions, or maybe we could describe this in terms of our definition from before. So we need to change the limits first. So we should express this guy in terms of our theta in this case. So it will be r equals to r sine theta. That means sine theta should be 1, or pi over 2. And for negative, it's negative pi over 2. And also, we could just write this function in terms of the theta. So it's gonna be 1 over r cosine theta, because 1 minus sine squared theta is cosine squared theta. So taking the square root of that, you get the cosine theta. And then after that, we could multiply this by the Jacobian of x over theta, or the dx over d theta, which is gonna be r cosine theta. So we multiply this by r cosine theta, multiply this by our d theta. And this turns out to be, so it turns out this r cosine theta will cross each other out. What we'll get is 2r times pi over 2 minus pi over 2, minus negative pi over 2. And this turns out to be 2 pi r, which is exactly the circumference of a circle. Great. So we could also try to figure out what's the area of a circle. And let's just do that. So to figure out the area of the circle, we could just take the sum again and do the same thing. So let's do that. We take the integral of the function, which is, in here, we want to take this to be our heights. Multiply that by the dx. So it's all of the heights times the small changes. And we will multiply this by 2 again. So the value here will be the square root of r squared minus x squared. Now, solving this equation seems hard, but you could do the same substitution again. Let's just do x equals to r sine theta. So it's 2 negative pi over 2 towards pi over 2. We could substitute then straight away. It's r cosine theta. Multiply that by the Jacobian, which is r cosine theta, times d theta. So this is 2r squared integral of negative pi over 2 until pi over 2 cosine squared theta d theta. Now, for you who are not really familiar with cosine squared theta, it is actually the same thing as 1 plus sine 2 theta, no, cosine 2 theta, over 2. So we could substitute that in. We would get r squared integral negative pi over 2 towards pi over 2, 1 plus cosine theta, d theta, 2 theta, d theta. And solving the integral, it's r squared to the integral of, that's theta, that means it's pi, so it's pi over 2 minus pi over 2. So we'll just separate this into 2. And then the cosine 2 theta, it's going to be sine 2 theta over 2. You could just check this straight away. And it turns out that this value is 0. So what we get here is pi r squared, which is exactly the area of a circle. So now I want to introduce to you a final trick. But before we get started on this trick, I will try to discuss the situation first. So maybe this integral is not solvable because because it's not really known as to how do you substitute it. But it is a known integral, so it goes from 0 to infinity. So this integral is very well known, and the answer is 1/2 over the square root of pi over a. But the way that we will actually solve this is by taking multivariable calculus, which I will later discuss on the next video. But in here, we will just take this to be a known quantity. And we could also do the same thing, but instead for x e to the power of negative a x squared dx. And what's this? This integral is the value of... So we could just try to solve this straight away, because it's an easy integral. So we could just straight away guess. I mean, you could also use substitution, but guessing this is pretty easy. So we could just assume e to the power of negative a x squared. Take the derivative, it will be the 2x. But that means that we need to divide it by 2, a, and I think the rest should follow. So it's negative 2a, so it's the negative of this value. It should be the negative of this value. Integrate that from 0 to infinity. So putting the values in, what you would get here is 1 over 2a. Now, okay, so this is simple, but maybe let's try to see if we could solve, in general, integral from 0 to infinity of x to the power of n e to the power of negative a x squared dx. What's the value of this? So let's introduce the theory as well as the proof. So let's say that this is the function a, which is the integral from 0 to infinity of our function of x to the power of n e to the power of negative a x squared dx. Fn. Let's just state that to be that. So this will be denoted as the integral from 0 to infinity of function x and a, since it doesn't only depend on x, but it also depends on our a, because this is our independent variable. So we have something like this. And let's try to solve. What about if we try to take the derivative of this function with respect to a? So we'll just use the definition. So it's the function a plus delta a minus function of a. Divide the entire thing by the change of a. This will equal to the integral from 0 to infinity of function x and a plus delta a dx minus the integral from 0 to infinity of function x comma a dx. Divide the entire thing by the delta a. So what you get in here is that you could just put the entire thing in. It's actually the function x comma a plus delta a and the other guy. And just by assuming the delta a is pretty much not changing with respect to x, as if a and x are independent of each other, what we could write is that this is the df x comma a over dA dx equals to df over dA. So with this, we could actually start to think of certain uses of this. So let's try to solve, let's say, I3, let's say. No, let's just do I2. So I2 will be defined to be the integral of 0 to infinity of x squared e to the power of negative a x squared. So we could just try to figure out what is this value exactly. So if we try to refer this from I0, which value is 1/2 to the square root of pi over a. If we take the derivative of this would be 1 over 2. Square root pi is still at the top, and then the square root of a at the bottom will become this. So it's negative 1 over 4a to the square root of pi over a. Wait, is that correct? It looks like it's correct. Now, this value should also equal to, so okay, this is the di0 over dt, dA. But this should also equal to the derivative of the integral. So from 0 to infinity of our small, well, not really small, but our function. And we could just take the derivative straight away. So it's e to the power of negative ax squared. And then we derive it with respect to a. So it's going to be negative x squared in here. So what we see here, this is the negative I2, and this equals to the negative 1 over 4a to the square root of pi over a, which means our I2 is 1 over 4a to the square root of pi over a. This is our value. So it is pretty useful if you have this dummy variable for you to actually take derivatives, or just to take the derivatives to figure out what's the next values. So there are more examples of using this kind of trick to solve certain integrals, but I will leave most of the practice to you all, because most of these questions comes from the book itself. So I hope that you would actually use this theory for you to solve each of these problems. So thank you very much for watching this video, and I hope this helps you a little bit more about understanding the mathematics behind physics and how do you utilize these tricks for you to solve your physical system. So thank you very much for watching, and don't forget to like and subscribe, and also please share this to your friends who really need to understand the mathematics behind physics in a much more clearer understanding. So thank you very much, and I'll see you on the next video.